In physics, heat is energy that spontaneously passes between a system and its surroundings in some way other than through work or the transfer of matter. When a suitable physical pathway exists, heat flows spontaneously from a hotter to a colder body. The transfer can be by contact between the source and the destination body, as in conduction, or by radiation between remote bodies, or by conduction and radiation through a thick solid wall, or by way of an intermediate, fluid body, as in convective circulation, or by a combination of these. Because heat refers to a quantity of energy transferred between two bodies, it is not a state function of either of the bodies, in contrast to temperature and internal energy. Instead, according to the first law of thermodynamics, heat exchanged during some process contributes to the change in the internal energy, and the amount of heat can be quantified by the equivalent amount of work that would bring about the same change. While heat flows spontaneously from hot to cold, it is possible to construct a heat pump, a refrigeration system that does work to increase the difference in temperature between two systems. Conversely, a heat engine reduces an existing temperature difference to do work on another system. Historically, many energy units for measurement of heat have been used. The standards-based unit in the international system of units is the joule. Heat is measured by its effect on the states of interacting bodies, for example, by the amount of ice melted or a change in temperature. The quantification of heat via the temperature change of a body is called calorimetry, and is widely used in practice. In calorimetry, sensible heat is defined with respect to a specific chosen state variable of the system, such as pressure or volume. Sensible heat causes a change of the temperature of the system while leaving the chosen state variable unchanged. Heat transfer that occurs at a constant system temperature but changes the state variable is called latent heat with respect to the variable. For infinitesimal changes, the total incremental heat transfer is then the sum of the latent and sensible heat. History. Physicist James Clerk Maxwell, in his 1871 classic theory of heat, was one of many who began to build on the already established idea that heat has something to do with matter in motion. This was the same idea put forth by Benjamin Thompson in 1798, who said he was only following up on the work of many others. One of Maxwell's recommended books was Heat as a Mode of Motion, by John Tyndall. Maxwell outlined 4 stipulations for the definition of heat. It is something which may be transferred from one body to another, according to the second law of thermodynamics. It is a measurable quantity, and so can be treated mathematically. It cannot be treated as a material substance, because it may be transformed into something that is not a material substance, e.g., mechanical work. Heat is one of the forms of energy. From empirically based ideas of heat, and from other empirical observations, the notions of internal energy and of entropy can be derived, so as to lead to the recognition of the first and second laws of thermodynamics. This was the way of the historical pioneers of thermodynamics, transfers of energy as heat between two bodies. Referring to conduction, Partington writes, if a hot body is brought in conducting contact with a cold body, the temperature of the hot body falls and that of the cold body rises, and it is said that a quantity of heat has passed from the hot body to the cold body. Referring to radiation, Maxwell writes, in radiation, the hotter body loses heat, and the colder body receives heat by means of a process occurring in some intervening medium which does not itself thereby become hot. Maxwell writes that convection as such is not a purely thermal phenomenon. In thermodynamics, convection in general is regarded as transport of internal energy. If, however, the convection is enclosed and circulatory, then it may be regarded as an intermediary that transfers energy as heat between source and destination bodies, because it transfers only energy and not matter from the source to the destination body. Practical operating devices that harness transfers of energy as heat. In accordance with the first law for closed systems, energy transferred solely as heat leaves one body and enters another, changing the internal energies of each. Transfer between bodies of energy as work is a complementary way of changing internal energies, though it is not logically rigorous from the viewpoint of strict physical concepts. A common form of words that expresses this is to say that heat and work are interconvertible. Cyclically operating engines that use only heat and work transfers have two thermal reservoirs, a hot and a cold one. They may be classified by the range of operating temperatures of the working body relative to those reservoirs. In a heat engine, the working body is at all times colder than the hot reservoir and hotter than the cold reservoir. In a sense, it uses heat transfer to produce work. In a heat pump, the working body, at stages of the cycle, goes both hotter than the hot reservoir and colder than the cold reservoir. In a sense, it uses work to produce heat transfer. Heat engine. In classical thermodynamics, a commonly considered model is the heat engine. It consists of four bodies: the working body, the hot reservoir, the cold reservoir, and the work reservoir. A cyclic process leaves the working body in an unchanged state, and is envisaged as being repeated indefinitely often. Work transfers between the working body and the work reservoir are envisaged as reversible, and thus only one work reservoir is needed, but two thermal reservoirs are needed, because transfer of energy as heat is irreversible. A single cycle sees energy taken by the working body from the hot reservoir and sent to the two other reservoirs, the work reservoir and the cold reservoir. The hot reservoir always and only supplies energy, and the cold reservoir always and only receives energy. The second law of thermodynamics requires that no cycle can occur in which no energy is received by the cold reservoir. Heat engines achieve higher efficiency when the difference between initial and final temperature is greater. Heat pump refrigerator. Another commonly considered model is the heat pump refrigerator. Again, there are four bodies: the working body, the hot reservoir, the cold reservoir, and the work reservoir. A single cycle starts with the working body colder than the cold reservoir, and then energy is taken in as heat by the working body from the cold reservoir. Then the work reservoir does work on the working body, adding more to its internal energy, making it hotter than the hot reservoir. The hot working body passes heat to the hot reservoir, but still remains hotter than the cold reservoir. Then, by allowing it to expand without doing work on another body and without passing heat to another body, the working body is made colder than the cold reservoir. It can now accept heat transfer from the cold reservoir to start another cycle. The device has transported energy from a colder to a hotter reservoir, but this is not regarded as being by an inanimate agency. Rather, it is regarded as by the harnessing of work. This is because work is supplied from the work reservoir, not just by a simple thermodynamic process, but by a cycle of thermodynamic operations and processes, which may be regarded as directed by an animate harnessing agency. Accordingly, the cycle is still in accord with the second law of thermodynamics. The efficiency of a heat pump is best when the temperature difference between the hot and cold reservoirs is least. Functionally, such engines are used in two ways: distinguishing a target reservoir and a resource surrounding reservoir. A heat pump transfers heat to the hot reservoir as the target from the resource surrounding reservoir. A refrigerator transfers heat from the cold reservoir as the target to the resource surrounding reservoir. The target reservoir may be regarded as leaking. When the target leaks hotness to the surroundings, heat pumping is used. When the target leaks coldness to the surroundings, refrigeration is used. The engine's harness work to overcome the leaks. Macroscopic view of quantity of energy transferred as heat. According to Planck, there are three main conceptual approaches to heat. One is the microscopic or kinetic theory approach. The other two are macroscopic approaches. One is the approach through the law of conservation of energy taken as prior to thermodynamics, with a mechanical analysis of processes, for example in the work of Helmholtz. This mechanical view was taken in this article as currently customary for thermodynamic theory. The other macroscopic approach is the thermodynamic one, which admits heat as a primitive concept, which contributes, by scientific induction, to knowledge of the law of conservation of energy. This view is widely taken as the practical one, quantity of heat being measured by calorimetry. Bailyn also distinguishes the two macroscopic approaches as the mechanical and the thermodynamic. The thermodynamic view was taken by the founders of thermodynamics in the 19th century. It regards quantity of energy transferred as heat as a primitive concept coherent with a primitive concept of temperature, measured primarily by calorimetry. A calorimeter is a body in the surroundings of the system, with its own temperature and internal energy. When it is connected to the system by a path for heat transfer, changes in it measure heat transfer. The mechanical view was pioneered by Helmholtz and developed and used in the 20th century, largely through the influence of Max Born. It regards quantity of heat transferred as heat as a derived concept, defined for closed systems as quantity of heat transferred by mechanisms other than work transfer, the latter being regarded as primitive for thermodynamics, defined by macroscopic mechanics. According to Born, the transfer of internal energy between open systems that accompanies transfer of matter cannot be reduced to mechanics. It follows that there is no well-founded definition of quantities of energy transferred as heat or as work associated with transfer of matter. Nevertheless, for the thermodynamical description of non-equilibrium processes, it is desired to consider the effect of a temperature gradient established by the surroundings across the system of interest when there is no physical barrier, a wall between system and surroundings, that is to say, when they are open with respect to one another. The impossibility of a mechanical definition in terms of work for this circumstance does not alter the physical fact that a temperature gradient causes a diffusive flux of internal energy, a process that, in the thermodynamic view, might be proposed as a candidate concept for transfer of energy as heat. In this circumstance, it may be expected that there may also be active other drivers of diffusive flux of internal energy, such as gradient of chemical potential which drives transfer of matter, and gradient of electric potential which drives electric current and iontophoresis. Such effects usually interact with diffusive flux of internal energy driven by temperature gradient, and such interactions are known as cross-effects. If cross-effects that result in diffusive transfer of internal energy were also labeled as heat transfers, they would sometimes violate the rule that pure heat transfer occurs only down a temperature gradient, never up one. They would also contradict the principle that all heat transfer is of one and the same kind, a principle founded on the idea of heat conduction between closed systems. One might try to think narrowly of heat flux driven purely by temperature gradient as a conceptual component of diffusive internal energy flux. In the thermodynamic view, the concept resting specifically on careful calculations based on detailed knowledge of the processes and being indirectly assessed. In these circumstances, if perchance it happens that no transfer of matter is actualized, and there are no cross-effects, then the thermodynamic concept and the mechanical concept coincide, as if one were dealing with closed systems. But when there is transfer of matter, the exact laws by which temperature gradient drives diffusive flux of internal energy, rather than being exactly knowable, mostly need to be assumed, and in many cases are practically unverifiable. Consequently, when there is transfer of matter, the calculation of the pure heat flux component of the diffusive flux of internal energy rests on practically unverifiable assumptions. This is a reason to think of heat as a specialized concept that relates primarily and precisely to closed systems, and applicable only in a very restricted way to open systems. In many writings in this context, the term heat flux is used when what is meant is therefore more accurately called diffusive flux of internal energy. Such usage of the term heat flux is a residue of older and now obsolete language usage that allowed that a body may have a heat content. Microscopic view of heat. In their kinetic theory, heat is explained in terms of the microscopic motions and interactions of constituent particles, such as electrons, atoms, and molecules. The immediate meaning of the kinetic energy of the constituent particles is not as heat. It is as a component of internal energy. In microscopic terms, heat is a transfer quantity, and is described by a transport theory, not as steadily localized kinetic energy of particles. Heat transfer arises from temperature gradients or differences, through the diffuse exchange of microscopic kinetic and potential particle energy, by particle collisions and other interactions. An early and vague expression of this was made by Francis Bacon. Precise and detailed versions of it were developed in the 19th century. In statistical mechanics, for a closed system, heat is the energy transfer associated with a disordered microscopic action on the system, associated with jumps in occupation numbers of the energy levels of the system, without change in the values of the energy levels themselves. It is possible for macroscopic thermodynamic work to alter the occupation numbers without change in the values of the system energy levels themselves. But what distinguishes transfer as heat is that the transfer is entirely due to disordered microscopic action, including radiative transfer. A mathematical definition can be formulated for small increments of quasi-static adiabatic work in terms of the statistical distribution of an ensemble of microstates. Estimation of quantity of heat. Quantity of heat transferred can be measured by calorimetry, or determined through calculations based on other quantities. Calorimetry is the empirical basis of the idea of quantity of heat transferred in a process. The transferred heat is measured by changes in a body of known properties, for example, temperature rise, change in volume or length, or phase change, such as melting of ice. A calculation of quantity of heat transferred can rely on a hypothetical quantity of energy transferred as adiabatic work and on the first law of thermodynamics. Such calculation is the primary approach of many theoretical studies of quantity of heat transferred. Latent and sensible heat. In an 1847 lecture entitled On Matter, Living Force, and Heat, James Prescott Joule characterized the terms latent heat and sensible heat as components of heat, each affecting distinct physical phenomena, namely the potential and kinetic energy of particles, respectively. He described latent energy as the energy possessed for a distancing of particles where attraction was over a greater distance, i. a form of potential energy, and the sensible heat as an energy involving the motion of particles are what was known as a living force. At the time of Joule, kinetic energy either held invisibly internally or held visibly externally was known as a living force. Latent heat is the heat released or absorbed by a chemical substance or a thermodynamic system during a change of state that occurs without a change in temperature. Such a process may be a phase transition, such as the melting of ice or the boiling of water. The term was introduced around 1750 by Joseph Black as derived from the Latin latere, characterizing its effect as not being directly measurable with a thermometer. Sensible heat, in contrast to latent heat, is the heat transferred to a thermodynamic system that has as its sole effect a change of temperature. Both latent heat and sensible heat transfers increase the internal energy of the system to which they are transferred. Consequences of Black's distinction between sensible and latent heat are examined in the Wikipedia article on calorimetry. Specific heat, also called specific heat capacity, is defined as the amount of energy that has to be transferred to or from one unit of mass or amount of substance to change the system temperature by 1 degree. Specific heat is a physical property, which means that it depends on the substance under consideration and its state as specified by its properties. The specific heats of monatomic gases are nearly constant with temperature. Diatomic gases such as hydrogen display some temperature dependence, and triatomic gas still more. Relation between heat and temperature. Before the discovery of the laws of thermodynamics, quantity of energy transferred as heat was measured by changes in the states of the participating bodies. Some general rules, with important exceptions, that will be noted in following paragraphs of this section, can be stated as follows. Most bodies, over most temperature ranges, expand on being heated. Mostly, heating a body at a constant volume increases the pressure it exerts on its constraining walls, and increases its temperature. Also mostly, heating a body at a constant pressure increases its volume, and increases its temperature. Beyond this, most substances have three ordinarily recognized states of matter, solid, liquid, and gas, and a fourth less obviously recognized one, plasma. Many have further, more finely differentiated, states of matter, such as for example, glass and liquid crystal. In many cases, at fixed temperature and pressure, a substance can exist in several distinct states of matter in what might be viewed as the same body. For example, ice may float in a glass of water. Then the ice and the water are said to constitute two phases within the body. Definite rules are known, telling how distinct phases may coexist in their body. Mostly, at a fixed pressure, there is a definite temperature at which heating causes a solid to melt or evaporate, and a definite temperature at which heating causes a liquid to evaporate. In such cases, cooling has the reverse effects. All of these, the commonest cases, fit with the rule that heating can be measured by changes of state of a body. Such cases supply what are called thermometric bodies, that allow the definition of empirical temperatures. Before 1848, all temperatures were defined in this way. There was thus a tight link, apparently logically determined, between heat and temperature, though they were recognized as conceptually thoroughly distinct, especially by Joseph Black in the later 18th century. There are important exceptions. They break the obviously apparent link between heat and temperature. They make it clear that empirical definitions of temperature are contingent on the peculiar properties of particular thermometric substances, and are thus precluded from the title absolute. For example, water contracts on being heated near 277 K. It cannot be used as a thermometric substance near that temperature. Also, over a certain temperature range, ice contracts on heating. Moreover, many substances can exist in metastable states, such as with negative pressure. that survive only transiently and in very special conditions. Such facts, sometimes called anomalous, are some of the reasons for the thermodynamic definition of absolute temperature. In the early days of measurement of high temperatures, another factor was important, and used by Josiah Wedgwood in his pyrometer. The temperature reached in a process was estimated by the shrinkage of a sample of clay. The higher the temperature, the more the shrinkage. This was the only available more or less reliable method of measurement of temperatures above 1000 degrees Celsius. But such shrinkage is irreversible. The clay does not expand again on cooling. That is why it could be used for the measurement, but only once. It is not a thermometric material in the usual sense of the word. Nevertheless, the thermodynamic definition of absolute temperature does make essential use of the concept of heat, with proper circumspection.